And what question do you have?
The first one is on 8.1.
Okay, let me get something to hold my place. 8.1.
Number 5.
Okay. You have the page number?
It's 206.
206. Okay. Thought I was close. Oh, at the bottom of the page. And which one?
Number 5.
Number 5, the one without a number, right?
Right.
Okay.
I think what really confuses me is when they don't give, like, this one is totally different from number 3, so I'm kind of confused on that.
Yeah. Well, they're asking, they gave you certain things and asking for a different one. So
right.
Number 5, let me get my pen set up. All right. This is page 205. This is problem set 8.1, and this is number 5. Okay. And here's what's given. F is equal to 25,700 newtons. 25,700 newtons. Quite a force, by the way. The displacement is given by 238 meters. Okay, that's a pretty long distance, too. The work done was 5.57 times 10 to the 6. That's a lot of joules.
Right.
Okay? Well, a joule is a pretty small unit. Okay? And what we're looking for is what is the angle theta. Now, with nothing else to go on, that's a little nebulous. But if you turn back to just one page, you'll see and this is the unknown here. Here's what we've got. Work is equal to force times displacement times the cosine of the angle theta in between. Now, this is requiring a concept you may not be familiar with, so I'm glad you asked this. I don't think you'll see one like this on the test, but you might. I don't recall that there is. Okay, what you're looking for is the theta here.
Yeah.
Okay, so, and you know the other 3 entities, so what we want to do is isolate the theta. So let's divide both sides by force and displacement. Okay, that wipes out force on this side, wipes out displacement on this side. All right, so that gives us cosine of theta is equal to the work divided by force times displacement. Okay. Now here's probably what you don't, I'm guessing you haven't ever done before. Doing what they call an inverse cosine or an arc cosine. Have you got your calculator? Okay. Do you see your cosine key?
I do.
Okay. Just above the cosine key is one that says cosine with a -1 or ARC cosine.
Right.
Cosine of the -1? Okay. Now, what you do here then, and here's how you actually write it. You undo the cosine by that inverse cosine. So it'd be the inverse cosine of the work divided by force times displacement. Okay. Now let me plug in the values. Okay. So this is inverse cosine of 5.57 times 10 to the 6th. Now what is a joule? Okay.
Joule is
okay, it's a Newton meter, and a Newton is a kilogram meter per second squared, so it's a times a meter is a kilogram meter squared per second squared. That's what a joule is. Okay? Right. Now, force is a Newton. That's 25,700, and actually, let me go back and make this a lot easier, because I was thinking we're going to have to cancel. Let's just call this a Newton meter up here then. A joule is a Newton meter, so it's going to be a Newton meter. Okay, makes it much easier. Okay, and your force is in newtons, and your displacement is in meters, 238 meters. All right, notice all your units disappear, which is good because the cosine of an angle is a dimensionless quantity. Okay, so the inverse cosine has to work on a dimensionless quantity. So I don't know your syntax on your calculator. Do you have a calculator too? Does it have an inverse cosine, or is it your phone? Which are you using? Calculator or your phone? Calculator. Okay. Did you find the inverse cosine key? Let me take a look. Okay. All right. So you press the second and that cosine key. Yeah, that. And see, that opens it up. Okay. Now, let me see yours. All right. There's your cosine key. You see that inverse cosine right above it? Cosine to the -1. And you use your shift to get that. So shift cosine. Open a parentheses. Okay, where's it? So why don't you open a parentheses? All right. Yours already open a parentheses, right?
Mm-hmm. How do I do the power on here?
Oh, okay. I'll get to that in a minute. Have you typed in? Now, actually, open. No. Okay. No, it's fine. 5.57. Did you do that? Okay. Have you done 5.57? Okay, now here's how to do scientific notation. Let me hold your calculator just a moment. My eyes are not good. Okay, you see this EE key?
Okay.
Okay, so again, that second EE. Okay, let me see yours. Different calculators have different keys for it. Okay. Look.
Oh, I think it did something else. Okay, you do 10, and then you do second.
Hang on a minute, because there's another little trick we need to know.
Okay. Yeah, let me go back.
Is it EE or EXP key? My eyes are bad, so let me see. I do not see this on your calculator. Okay. I think what you use is 10 to the x. Okay. I don't know if you need to do a times 10. Let me just try it. Shift into the x. No, that's right. I don't think. Yeah, that's right. And then do a 6. Okay. And then division by. Now you need to open a second set of parentheses for that denominator. And then type in the 25,700 and then times 238. Then close that inner parentheses. Then close the outer parentheses. Okay. Did yours work?
Yeah, I
Okay, no,
yeah, I
okay.
tried to do that, but it,
No, okay. Did you put the times in?
yeah,
Okay,
take it
let's
out.
do that, yeah. So you do, EE is right there. Second, EE, and see that stands for, that's where you put in the 6.
Oh, okay.
Okay.
And then close parentheses.
No, not yet.
Okay.
You got to do your division, and then your 25, okay, and then before you divide, open another parentheses,
Okay, so
and then do your 25,700 times 238, then close that parentheses, then close the cosine parentheses, and then press enter. Oh, I forgot to tell you one other thing.
Yeah, see, I did something wrong because look what I got.
Okay.
I have to start all over.
Oh, do you? Okay. No, you don't. No, okay, not. Okay. It's 238 times. No, oh, wait. Wait, oh, I'm sorry. Okay. All right. See, right before that, after the division sign, that's where you open the parentheses.
Okay, so
Then
division,
there's 25,700
Okay.
times 238. 238. Then you close the denominator parentheses. Then you do close the inverse cosine parentheses. And now you get what you get.
24.
Yeah, 27.4 degrees. Did you get that?
24.4.
24. Perfect. Way to go. Okay.
Okay,
Well, I forgot
let
to
me-
tell you get in degree mode first, but I'll be we're in degree mode.
Okay, let me write this down so I can remember.
Yeah. All right. Now, we're doing, they ask about on page 205, problem set 8.1, number 5, and that's what we're doing. That's called an inverse cosine because you're looking for the angle. If you knew the angle, you use cosine. If you don't know the angle, you use inverse cosine. And everything else gets done inside. Okay. And does anyone check the back of the book to see if that's what the angle was? I think I'm right there. Nope, I'm not yet. Right here. This is 8.1, number 5, 24.4 degrees. Perfect. Yeah, without having had trig, it's hard to have got that to work out right, but to know how to do that. But that is how you do it. The cosine, you operate on an angle, you get a number. The inverse cosine operates on a number to give you an angle, and that's what you did here. Second? Okay. What's that? I can't hear.
I never take anything over 110.
Okay. Well, hopefully you're not going to see one of those on the test. I can't recall that there was one. Maybe in a later chapter, but we'll do several of those first. Okay. Any others?
Yes, I have one more from next chapter. Number 9.
Same section?
Mm-hmm.
Okay. Let's see if oh, there. Yeah, number 9. On the next page, all right. All right, to clear this, you okay with it? Oh, I forgot to mark you here because I was off and running. Trent, right?
Yes, sir.
Okay. All right. Now, I'm going to clear this screen, and the only thing that changes is page 207, right?
Yes. Now, when they give an example in this book, and the formulas for some of these,
Yeah.
are you able to use the formulas for most of the homework problems?
I would think so, but I haven't worked all of them, so I don't know for sure. Right. Okay. Is this number 9 you said?
Mm-hmm.
Okay. A worker lifts 75 concrete blocks. He's going to be sore tomorrow. Okay. A distance of 1.5 meters. Okay. So this is your S, distance. I've lost it. Yeah, there it is. To the bed of a truck. Each block has a mass of 4 kilograms. 4.00 kilograms each, which is, I found, hard to believe. Not that it has that mass, but that each one of them has precisely 4.00 kilograms. That's a little artificial, okay? How much work is done to lift all the blocks to the truck bed? So we're looking for work. Now remind me what work is.
Work is the force.
Force.
Times displacement.
Displacement. Perfect. Okay, we're not given a force. What is this 4 kilograms each? What's that a measure of? No, that's not. Kilogram measures. No, kilogram. Kilogram is a unit. That measures what? What entity? What quantity does it measure? It measures the mass.
Okay, mass.
Okay, so we're given the mass. Okay, or we're given the mass of 1. So number 1, you got to multiply it by 75. So 4 times 75 is 300, I believe. 300 kilograms. That's the mass of the 75 blocks. Okay? He's lifting each one 1.5 meters. Okay, we've got to get the force. What force is he having to overcome to lift those blocks up into the truck? The force due to? Second? Okay, the mass of the blocks is important, but what else is important? What is he doing when he's lifting the blocks? What is he really lifting? What force is that?
The bricks.
The what?
Brick.
Okay, it's the brick, okay, but what is the force involved that he's having to exert to lift those 4 kilogram blocks? What is pulling down on the blocks? Must be something, or else they'd be floating away. Gravity.
Yeah.
Okay. Now, how do you relate mass and gravity to get a force? Yes, you do. Mass times the acceleration due to gravity. Mass times acceleration is the force due to weight. That is the weight of the block. That's the force he's having to overcome, the weight of the blocks. And that's mass times acceleration due to gravity, which in this case is 300 kilograms times, and remember what acceleration due to gravity is 9.80 meters per second squared. Acceleration is a distance per time squared, so it's distance per meter squared. So that will give the force, okay? So that will be 300 kilograms times 9.80 meters per second squared times the displacement, which is 1.50 meters. That's how high he had to lift it. That's about chest level, because waist level is about 1 meter, and then chest level would be about another. So that's a pretty hefty job. Okay, and what would you get there? 4410. And that would be kilogram meter squared per second squared, which is a joule. Perfect. Okay, and that 0 is not significant. 4410 joules. Now, hopefully they don't count the 75 blocks as a significant digit. That doesn't make any sense. This is number what? 9? Yeah, 4410 joules. That's it. Okay? Because 75 is how many blocks you got at that many kilograms, so that gives you your 3 significant digits. Even though 75 is listed, because you don't load a fraction of a block. 75 blocks. Okay. Does that answer that one?
Yeah. So that at the top right there where you got, is that 8?
Where's this?
It's to the 4.0.
Above it or beside it?
Right. Yeah,
Right here?
75.
75 times 4 is 300. We multiply 75 blocks for 4 kilograms each. 4 kilograms was the mass of each block, so multiply by 75 blocks, and that gives you the total mass that he lifted. Okay. And mass times acceleration due to gravity is then the weight, and multiply the weight by the distance. That gives you the work. No angles involved with this because it was a straight lift. Okay. Any others?
I have one for you next week.
Okay. That's a promise or a threat? Okay.
Look, I'll try to get the ones that's on the examples on the test because, like, I have to be able to go back and work these out.
Okay. Now, last time we started dealing with this table on page 221. And we talked about how to do it. Did any of you carry it any further, or did you need me to go over it a little bit more?
Yeah, probably so, because I haven't got to that part yet.
Okay. So I'm going to clear the screen. So we'll start on the table again. Okay? All right, just a little bit of a review. It says, drop a 5 kilogram mass from a hot air balloon 400 meters above the ground. Find its kinetic energy, its potential energy, and the sum of the kinetic and potential energies at 1 second intervals until the mass hits the ground. Assume no air resistance. Okay? So they give you the mass, and it's only one mass you're dropping, not 75 of them. And this is 5.000 kilograms. Why they got forcing of it digits now, I'm not sure. Because the acceleration due to gravity, we know, is 9.80 meters per second squared. So it doesn't matter that last zero on the 5.000. All you can use is 3 anyway. But it's okay. All right. Now, it says use this table. The first column in the table is time. That will be measured in seconds. The second table is displacement, and that's measured in meters. The third column is the velocity, measured in meters per second. The next is the kinetic energy, E sub k, which, by the way, is 1/2 mv squared. Okay, just to remind you, that is your, and that's measured in joules. Okay, the next one is your H. That's how high you are above, let's see, how high the block is above the ground. That would be in meters. And then you have the potential energy, gravitational potential energy, and a reminder. Anyone remember what that formula was? mgh. Okay? All right. And that will also be in joules. And then your total energy, I'm going to call it mechanical energy because that is your total energy here, and that will also be in joules. Now, anyone remember what mechanical energy is? You sum the kinetic with the potential. The sum of those two. Okay. Now, yeah, is energy due to motion. That's why velocity is involved in that. All right. Remind me of your name, please. Okay, Latondria. Okay. Got it. Okay. Okay. We're doing where we left off last time, because we've done a few problems. You can go back and watch the video and get those problems. We're doing this, dropping the mass from a, what was it, did they say? Just a mass, from a hot air balloon and watching it fall. Now, the hot air balloon is initially at 400 meters above the ground. So, I haven't left very much room here. So, the balloon here with the basket under it, and that's where you're dropping. The ground is down here, if I could get it to draw, 400 meters above the ground. They put 0.0 meters. Okay. Again, 4 significant digits, they only have room. We're only going to be able to produce 3. Though their table, they do them in 4s and beats me. Okay. Now, at 0 seconds, right when you release it, it hasn't traveled any distance at all, right? So that's 0 meters. Its velocity, 0 meters per second. Now, how do you know that? It says you drop the mass. You don't throw it. If you throw it, you give it an initial velocity. If you drop it, it leaves from 0. So what is kinetic energy at the top? One half mv squared. If velocity is 0, the kinetic energy is no. V is 0. 1 half mv squared. V 0. 0 squared is 0. 400 times 0 is 0. 1 half of that is 0 at 0. It has no kinetic energy right when you release it. It's going to start dropping, but it doesn't have any then. Its height at that point is your 400 meters, because that's how far you are above the ground. Okay? His potential energy there, what is it?
This is a tutorial showing you how to change the quantity.
Okay, no problem. I thought Alexa was giving you the answer. Okay. All right. Mason, got it. Thought that's who you were, but I didn't want to guess. Marked wrong. Okay. Okay, we started the day doing a couple problems from earlier in the chapter, so those are on the YouTube video, or will be on the YouTube video. Now we're picking up where we left off last time, which is this hot air balloon dropping a mass to the ground. Okay, we've already determined that at t equals 0 second, that's where we start. Hasn't fallen anywhere. The velocity is 0. Kinetic energy is 0. The height is 400 meters, because that's how far it was to begin with. Now we're trying to find the potential energy at the top. I wrote down the formula for you. Second, this is on page 221. This is example 2. Just plug in your mass of 5. No, it's not 5,000. It's 5.000.
Oh, okay.
It's 5 kilograms times 9.80 meters. You can just put 9.8 meters times 400. Pretty significant. I think we did this last time, but I'm not sure.
19,600.
That's it, exactly. 19,600 joules. And the mechanical energy is the sum of kinetic and potential. Since kinetic was 0, this was 19,600. Then the total mechanical energy is 19,600. And they put a bar over that fourth 0. I don't think that's legitimate, because your acceleration due to gravity only has 3 digits. But I'm not going to argue with them. Okay. Now they do it each second. So we're going to do 1 second later. Okay, and they put 1.000 seconds. Okay, exactly 1 second later, to the nearest thousandth of a second. How far has it fallen? That's what the S is. Now here's where you sort of got to stop and think a moment. Okay? The acceleration due to gravity is 9.80 meters each second. Okay? So actually, I don't think the S is the easy thing to do here. I think the velocity is probably the next easiest thing to do. So if 1 second later, the velocity increases by 9.8 meters each second. So this will be 9.80 meters per second. Because that's what acceleration is. How much change of velocity do you have each second? 9.8 meters per second. Okay. Now, to get the S, I probably should have put this one in here. They give you the formula up in the thing above. In column 2, use S is equal to 1/2 gt squared. Okay? Where g is the acceleration due to gravity. Okay? So if g is 9.8, half of that is 4.9, and then 1 second squared is 1. So that would be 4.9, and they probably put an extra 0 on it. No, they just leave 4.9 meters. I don't know. I can't follow their rationale in their units, in their thing. Okay?
So you said we're supposed to square the which one?
Square the time.
Okay.
And the time was 1 second. Okay? So that gives you how far it fell. 4.9 meters. It's just simply 1/2 of 9.8 times 1. Okay? Now, this time it does have a velocity, 9.8 meters per second. Okay? So now it will have some kinetic energy. And that will be 1/2 the mass. The mass is 5, so that would be 2.5 kilograms times this velocity squared, 9.8 squared. So 2.5 times 9.8 squared. I'll be sure you square that velocity before you multiply by 5. Or 2.5. Your calculator will take care of it if you do it that way.
It's 240.1.
It's what? 240? So 240 joules. Perfect. Okay? Now, how high is it above the ground? Well, it was 400. It fell 4.9. So now that will be 395.6. Okay? You see, it was a height of 400 meters, right? Right. And it fell 4.9 meters. So now the difference of that is 395.6 meters. Right? Okay? So now that you know the height, you can calculate the new potential energy. A little bit less than it was before because it's fallen 4.9 meters. So that will be mass, 5, g, 9.8, height, 395.6. The mass is 5,
Okay, I got it.
g is 9.8, and the height was that we just calculated, 395.6. Three what?
359.9.
Okay, well, okay, yeah. So count 4 digits, because that's what they're using. Look to the right. It's a 9, so move that up to 360. That last digit is not significant, so don't ever put 1 there. That will be joules. Okay. Now, we calculated our kinetic energy and our potential energy completely separately, but let's add them together and see what you get. 19,360 plus 240. Absolutely. The mechanical energy is conserved. It does not change. The reason is we're ignoring air resistance. So all you have is an acceleration due to gravity, free fall. So yes, there should be no loss of energy.
This be on the test.
What's that?
This be on the test.
Not anything this complicated, but the pieces of it could be on there. Okay, now I'm not going to do all these. Okay, obviously it takes a while, but let's do 2 seconds. Okay, just to make sure we got it. Now you use this formula here, 1/2 gt squared. So that would be 1/2 of the acceleration due to gravity is 4.9 times 4 this time. 2 squared is 4. So 4.9 times 4. 19.6. That's how 60 they put. No, they don't. They just put 6. Okay. Meters. Okay. Then the velocity, we know that every second it goes up, the velocity increases by 9.8. So this will be 19.60 meters per second. Okay? Because just add another 9.8 to it. Because every second, the acceleration tells you every second it increases the velocity by 9.8 meters per second. That's what acceleration is. Now you take that, plug it into your kinetic energy. 1/2 the mass was a 2.5 times, now you square this one, 19.6 squared. So 2.5 times 19.6 squared. You get it?
You said 19.6?
1/2, okay, 1/2 of 5 is 2.5 times the 19.6 squared.
Oh, 960.
960. Perfect. Okay, how did you get your height? It's your initial height, which is 400, minus how far it fell. So at 2 seconds, it's fallen 19.6. So subtract that from 400. 400 minus 19.6. 380.4 meters. Now with that, you calculate your potential energy. Mass, which is 5, times g, which is 9.8, times this new height, 380.4. Eighteen.
639,
So that'll be 640.
yeah.
Okay? 18,640. You add that to your kinetic energy, 960, and what do you get? Don't you get?
384, right?
Yeah, add 960 to 18,640. This should be E sub k plus E sub p. Your kinetic energy plus your potential energy. Hopefully you can still get that 19,600. Is that right?
Yeah.
Yeah, perfect. And you see, that's how you go from all. You just keep going.
Well, that's a lot.
I know, it's a really time-consuming exercise.
That's a lot.
Okay? But at the end, when you get down to 9 seconds, you'll see you only have a little bit of potential energy left, and you can't possibly fall. The last time you fell about 83 meters, and now you only have a height of 3.1 meters, so you can't fall any further. So at the very bottom, it says t seconds would be 9.035 seconds, and that would be you fell 400 meters, velocity would be that, your kinetic energy, all of it kinetic energy, no height left, no potential energy left, so it's 19,600. Okay. To me, that's kind of a busy work problem. But doing it a few times gets in your head how you calculate distance, how you calculate velocity, how you calculate kinetic energy, how you calculate the height, how you calculate the potential energy, and then adding those two together. So unless you need to see another second or two done, you got the idea? Okay. Let's move on, and now we're ready for the next slide. And that next slide is here and there. All right. All right. If it'll come up, there it comes. Ever been on a roller coaster? Yeah. I have no desire ever to be on a roller coaster. I get sort of dizzy looking at it, you know. I'm afraid I'd throw up. Okay. I know. I'm just sort of a wimp when it comes to heights. Okay. What they do, this is as low as that roller coaster will ever go, or at least you hope that anyway, right? So that's your zero reference level. Okay? And what they do, they have a trolley or something that catches you and takes you up to point P, which is as high as you will ever go. Okay? And then from that point, they let you go. Okay? Now, what's happening to this roller coaster, it has its maximum potential energy right there because that's as high as you'll ever be above the reference level. Okay? And at that point, before you start down the hill, you're at zero velocity, basically. Okay? And it'll give you one last shove, and there you take off. So at zero velocity, no kinetic energy, all of it is potential energy, maximum height. Okay? And that's your total mechanical energy. So once you start going down the thing, you start losing potential energy, gaining kinetic energy, which means you're gaining speed like crazy, right? Okay. So when you get to point Q here, I don't know, they don't tell you what point Q is. It looks like you're more than halfway down, but wherever it is, at that point, whatever height is, that's your potential energy, mgh, whatever your mass was up there. You've lost that much potential energy. That means you gained that much kinetic energy, which means your speed increased. Now, right over here at R, you're basically back at your reference level, but you're on the other side of the track there, so you're as fast as you'll ever be. All of your potential energy that was there is now kinetic energy there. And you can use that formula. Remember, V is equal to the square root of 2g, right? 2gh, because the height matters. Okay? Then you go back up. Do you think you'll make it to here? Sure you will, because you'll still have kinetic energy to spare because you're not back up here. You still have all the same mechanical energy. Now part of it is kinetic and part of it is potential again. So you do the loop-de-loop to run, and then when you get here, they either stop you or you go on another loop. My guess is they'll stop you. Now, in reality, there's always a little bit of friction. So you'll never make it back up here if there was any friction at all. If there was zero friction, you'd just barely get back up there. But you know there's always friction. How do you know? You were on a roller coaster? Could you hear anything? The wind. But you also hear the tires on the track, don't you? And they're sort of going, you right? That's losing energy there. All that sound is produced by that. And if it's making bends, then they go when they go around the bend. Okay, that's losing energy. Okay, so yeah, you'll never make it back up to the top unless it was absolutely no friction. Then you'd make it all the way back up, and you'd have no air resistance. That's not very realistic. Okay.
They have a kind that goes backwards.
What's that again?
They have some that will take you backwards.
Oh, backwards. Oh, wow. I bet you that is a weird feeling, isn't it? Okay. what it doesn't say at the top because it cut off. It says work is done to take the roller coaster car from the beginning of the ride to the top. That was the trolley or the whatever it is that's pulling you up there. That was the work being done. The exact amount of work they did to get you up there, that is now your potential energy, okay, because you're not moving up there, okay, to the top structure to give its potential energy. After it leaves the peak of the ride, the sum of the potential energy and the kinetic energy is equal to, the sum of the potential energy and kinetic energy is equal at each point in the ride. Why? Because mechanical energy is conserved. We're assuming if there was no friction. So that means even though you're losing potential energy going down, you're gaining kinetic energy. But the sum is the same as it was at the top, which is the same as the work done at the very beginning. Now, have you ever been to the McWane Science Center? Okay. You know when you first come in, there's that big gadget there of all the balls rolling around and stuff. And basically that's the same type thing. If you notice somewhere in the middle there, there's a little elevator. And the balls come down and get on the thing, and it picks them up and takes them to the top, giving them potential energy. Then they push them, and then the rest of it is conservation of mechanical energy. Going around, banging into things. But every time it makes a noise or does something else, it will lose a little bit of energy. And it rolls to a stop at the bottom, and then that gives it the energy again, picking it back up. I can stand there and watch that thing go for a long time. It's just mesmerizing. Okay. Now, here is something else, and they really don't do anything with this. They mention, but because it's in the book, I'll mention it too, concept of elastic collisions. So I'll go back. Well, let's just get to the other slide. Second. This is on page 222. All right. And here's a definition. Well, it's not really a definition. It's a statement. Okay. In an elastic collision, okay, the total kinetic energy of the system before the collision equals the total kinetic energy in the system after the collision. I'm just going to put E sub k, that's what we're using for kinetic energy. If I could write, okay, let me try it one more time. The total kinetic energy before the collision, and it's of the whole system, let me clean that up. Of the system, the whole system, before the collision is the same or is equal to the total kinetic energy, E sub k, after the collision, of the system. Okay. That is an elastic collision. Okay. Now, what is an elastic collision? An elastic collision is one that when the two objects collide, neither one of them crinkle, or get dented or thing. They bounce off each other with the same energy, total energy that was happening before. One of the classic examples of that is billiard balls, pool balls. Those are usually really close to elastic collisions. Just because you hear them, you know there's a little bit of loss because they've made the sound, but that's not a lot of energy, just a little bit. And here's the deal, folks. When that break, the guy who's starting it hits the cue ball into that rack, all the kinetic energy is in the cue ball to begin with because all those others are at rest. They have zero kinetic energy. Then they all start moving around. The total kinetic energy before that collision equals the total kinetic energy after the collision. That's what we mean by elastic collision. The example they show in the book is backyard physics. Does anyone play croquet anymore? Do you even know what it is?
Yeah, I've seen
Okay, I've seen it too. We have a set in our garage that we found on the street, and my wife said, "Oh, this would be neat to have when the kids come over and stuff." And we never have taken it out of the garage. We just move it around in the garage, but never move it out. But those are supposed to be elastic collisions when the ball hits each other. They show the example in the book. Okay, there's another physics connection, landing on an aircraft carrier, and the picture shows here, they don't have a slide of it, so I can't show that, but that's what you have. The jets have a tail hook on the back of them. They have these steel cables across the deck, and the hook will grab one of those cables, and then with a lot of friction, they bring that thing to a stop. Because those are jet planes going at quite fast speeds, and they bring them to a stop before they run off the end of the ship. I was on an aircraft carrier when I was in the Navy, and one of the jobs that I had toward the end of my time was sort of overseeing the installation of a tactical support center. And this other aircraft carrier had one, so they launched me off I left from the field, took me out to sea. They caught me on the other one. They used the tail hook, but it was a pretty slow plane. It was a prop plane. So I got one carrier landing, and then they threw me off with a catapult off the other end to send me away. So I had one carrier takeoff. They were sort of fun. All right, but that ends for 8.4. So there are problems there. Do any of the odds 1 through 13. Do some of each type. Now, most of the rest of the chapter, 8.5, is alternative energy sources. We're not going to do a lot with that, but I'll just go over. The picture here at the bottom of the page is a wind farm. And the wind, those little windmills, you might call them, you see the back of them? There's a little thing sticking out. That's a generator.
What are those for?
They generate electricity. They catch the wind, turn the propellers, and then that generates electricity, and then they run that down underground, add it up, and send it on to the grid.
It looks like somewhere far out, like Arizona.
Yeah, it's, they don't say where this one is. When my wife and I were out west a couple of summers ago, she had professional meetings in Salt Lake, or near Salt Lake City, and it was my week off, and her meetings were only either on the weekend or end of the week or stuff like that. So we took a little time off and traveled out there, drove around. We got to see Yellowstone again, but it was so crowded we couldn't see much. And we went and drove through Idaho and a little bit of Montana and a little bit of Wyoming, all close, and Utah again. And we drove by some wind farms, and it was just amazing to see. They stand way high, and these were in a farmer's field. He was out there baling hay underneath them because they were way up there. So he was leasing that and getting money from that while he was still able to use his land to bale hay and feed his cattle. So we thought, pretty smart, okay? And you could just see those things are turning because it seems like the wind always blowing out there. So those are one type of alternative energy. That little thing sticking out the back of the center of it, that's the generator. The wind is turning the propeller. The propeller is making electricity. Okay. Then on the next page, you see it looks like a garage there, and that must be the side toward you is the south side, and they have the solar panels on top. We, Karen, had professional meetings in No. We just took no, let's see, I can't remember what the trip was about. But anyway, we were on the train traveling through southern Germany, okay? And we went by towns that just about every building on the south side of the building, houses, garages, whatever, had an array of solar panels. They were capturing this light from the sun, converting that to electricity. Now that is direct current, DC. Then they had to convert that to alternating current. The windmills produce alternating current to begin with, okay? So, but still the sun, when the sun shines, you can be producing electricity. Those are just two types of alternate, what do they call it? Alternate energy sources. Okay. And they talk about a wind turbine technician. I'm not really sure why they're talking about him there, but there's a picture. Evidently he is doing something to the wind turbine. So that ends the chapter. There's a glossary there with some of the terms in it. There's review questions that sort of are the conceptual type things. But the review problems, those will be most similar to what you have on the test. I can't remember if they have all the answers in the back or just the odds. In the review problems, they have all, I think. In the sections, they have odds, but the review problems, they have them all. So you can work any of those 1 through 15. You don't have to. What's that? Yeah, they'll be similar to what you would see on the test. Okay, so I'm going to close this off so I can show this last slide here. That's not what I wanted to do. Escape, that's what I wanted to do. Okay, and I'll actually go back. Okay, and here's the last slide of the chapter, which is a lot like the previous slide, only have a little more information on it. Okay.
Should we be going through most of the regular problems too throughout the sections?
I would say do what you feel like you need to do. If you feel like those sort of simple ones that will help get you ready, that would be a good thing to do. If the ones at the end, if those seem too simple and the ones at the end of the chapter are a little more challenging, those, do whatever seems best that you have time to do. Don't overwork this. Okay, take care. How's the foot going? Good. All right, good deal. Be safe. All right, so Les, I know that's probably not a very good answer, but the more you practice, the better you get at it, is what it comes down to. But don't cure yourself on it, okay? You don't need to do them all. Okay, here's a typical roller coaster type experience. Hopefully, I'm not on one of these, but you start here at 0 velocity, meaning you have 0 kinetic energy, right?
I don't think I'm going to get on that.
Me either. Okay. 60 meters off the thing, so that gives you all potential energy. mgh. Now, they didn't tell you what m was, so you don't know exactly. But whatever your mass is there, that multiplied by acceleration due to gravity times the height of 60 meters. All your energy is potential energy there. Now, you come down here, and you get to the bottom. You're going to be at maximum speed here. Maximum kinetic energy, 0 potential energy down here, because you're at the 0 reference level, because that's where you've measured your height from. But then you make a loop up here 20 meters off. So what you have is only 1/3 of your initial potential energy. That means 2/3 of your initial energy is now kinetic down here. Here, all of it was kinetic energy. So you have slowed a little bit, but you've only gone up 1/3 of the way. You come out of that loop and go up again, and this 30. So half of the energy you had here is now potential, half is kinetic. So you still have a pretty good speed there. Okay, you come down and get to maximum speed again, maximum kinetic energy, zero potential when you're down here at the bottom. But you go back up, and this time you're 2/3 of the way up. You should still make that loop. You still got enough energy to do so, and you have some speed here because you still have some kinetic energy, but then you make your way on down. At some point, they have to stop you. It depends on how much friction and other things this has, how much energy you might be losing. But if this is a real slick system with very little kinetic friction loss and minimum air resistance, then you could keep going for quite a ways that way. But you know you always lose some. Okay. That was just an applied concept. You can work through that if you'd like. It's not necessary, but you can if you'd like. All right, so that now ends Chapter 8. Whoa. I can't remember if I ran off enough. I don't think I did. I was going to do that when I got here today, but I got here late, so I just came in and started. Okay. Master. I wish I'd have thought of this. I should have given him his. Okay, I think I have enough for y'all, but I need to make more copies for the rest of them. Make sure I'm right on this. Okay. So here's your second test. That should be the master. Okay.
Moving right along.
Yeah.
No, I said moving along.
Oh.
I need to get A on
Sorry,
all
that's not
these
breaking the rules up. Okay, I've got to make more copies, but I'll try to do that at the end. Find the work done. Now let's see how many more I need before I forget it. 1, 2, 3, 4, 5. I need at least 5 more. Okay. All right. So we're through with Chapter 8. We're going to continue using this, but we're going on to Chapter 12. Okay. Now we're skipping 9, rotational motion. Yeah, that's a lot more physics than probably what you need. 10 is simple machines. Interesting stuff, but not anything you need for what you'll be doing. 11 is universal gravitational and satellite motion. I don't think y'all are going up in satellites, so you won't need that one. But Chapter 12 is what we call, it's the matter chapter, and basically, I can't remember how the syllabus read, but you do need basic concepts of matter. So that's what we're doing in this one. So let's go from current slide, and let's get started in 12. All right. Matter. We'll get to this in just a second. A few definitions first, so let me maybe go back. See, is there room? Not. Well, there's some room to write on here. Let's do it here so I won't have to be going back and forth between slides so badly. All right. Now, matter is anything that occupies space and has mass. Let me get my pen set up. Okay. Anything that occupies space and has mass. That covers just about everything, right? Okay. Energy is not matter. It doesn't occupy space. It has no mass. It's related to mass, but it doesn't have any mass itself. Forces are not matter, okay? Matter are the actual physical objects that occupy space and has mass. Okay. Now, when we're talking about matter, there are basically three ways we talk about matter. We're only going to mention two of them here. First is elements. Anyone know what elements are? Cannot be broken into anything smaller. Yeah, that's it, exactly. Element is a substance that cannot be separated into simpler substances. Okay. If I say the word periodic table, you know what I'm talking about?
Yeah.
Okay. Yeah. I think I've looked before and I can't find one in this book. Okay.
Carbon.
Yeah, carbon's in there. Hydrogen, helium, beryllium, boron, lithium. Let me see if I think I've looked before and I can't recall that I ever found periodic table, but let's see if they list it. OP. Periodic table 628 and 643. Let's see if it's in there. 628 and 643. Can't get my old fingers to work. No, they talk about the periodic table on 628, 643. I think I've done this before. Nope, that's when they give the glossary on the periodic table. Okay, so it's not in here. But if you can picture the periodic table.
It's in cubes, right?
Say again?
Isn't it in squares?
It is sort of a rectangular looking thing. You'll have hydrogen up here in row 1, and then way on the other side you have helium in row 1. Only two things in the first row. Yeah. Then the next row has two things here, lithium and beryllium, and then it skips a space and finally picks up with boron, carbon, nitrogen, oxygen, fluorine, and neon, I believe it is. Yeah. Okay? So there you'll have 8 things on the second row. Mm-hmm. Third row, just like the second row, it starts with sodium, magnesium, then you skip a bunch and come back to aluminum, and you go on from there. Phosphorus is there, a bunch of other things there. And ends with argon, I think, or something like that.
I think since in high school, I looked at it last year. I took chemistry and I ain't looked at it no more.
Okay. Well, what you have listed there, and there are around 100, 108, 98, something like that, somewhere around 100. Those are your elements. They can't be broken into any simpler substances. Argon is argon. Sodium is sodium. You can't break it down any smaller. They can combine with all sorts of things, but they can't break down into anything simpler. Those are your elements. Okay? Now, the next classification of things, if I can get my pen back here, is a compound. And if you think about it, what does that, the prefix com means with. Communicate is talk with. Com means with. So this is something combined with other things. So that's what a compound is. A substance containing 2 or more elements.
And don't ever get potassium. Potassium hurts. It burns bad.
If you ever touch it, I would think so.
Get it in IV,
oh my.
horrible.
Okay. Substances that made up or containing two or more elements. Okay, let's name a few substances that are pretty common. Can you think of any compounds that are fairly common? You mentioned potassium, that's an element. Potassium chloride would be a compound. And where is potassium? Say again? Say again?
Hydrogen chloride.
Hydrogen chloride, that's hydrochloric acid. That is a substance, that's a compound, one you don't want to mess around with either. Sulfuric acid, any of your acids, your bases like sodium hydroxide, you know. Ammonia, that's a perfect example. Breathing out, carbon dioxide, that's carbon and oxygen made up of elements. How about good old agua? Water. What is it? H2O, hydrogen and oxygen, made up of two or more elements. Okay? That's what a compound is. Now, there's one other that they usually talk about. We're not going to talk about it in this chapter, and that's a mixture. When we talk about compound, substances containing two or more elements, that means chemically containing them. They are tied together in a very special way. They become something completely new. Okay? A mixture is still sugar and water. Sweet water, okay? It's still water, it's still sugar. Nothing really has changed except it's dissolved in there. You know, so a mixture isn't a chemical combination. A compound, very different from its elements. Let me give you one example. I said potassium. Sodium chloride, okay? Sodium is an element. You'll never, I don't think you've probably, except maybe in a chemistry lab, ever see any pure sodium, because sodium is very reactive. In fact, sodium in the chemistry lab, here's where you'll see it. It'll be in a jar covered with oil, because the sodium is that little yellow blob at the bottom covered with oil. Why is it covered with oil? If it was ever exposed to air, which contains some moisture in it, it explodes. Yeah. What's that? Yeah. Yes, exactly. Because sodium is explosive when it touches water. I mean, just explosive. Okay. And so here and it's a metal. It's a very soft metal, and it's explosive. If you got it on your skin, it's going to blister it immediately, because it's going to interact with the water in your tissue and just destroy the tissue. Okay, and you'll get a bad burn right there. You know, just a little bit right there. So here we have a very reactive metal, and chlorine. Anyone know what chlorine is? It's another element. Okay, now that is a sort of like Clorox. We say it's chlorine, but it's actually a compound. But what chlorine is, sometimes you see it on tanker cars on a train or something, and it'll say chlorine gas. It's a green gas, and if one of those trains ever derails and that chlorine gas tank leaks, everybody is evacuated, because it's a green gas that's very poisonous. So here we have sodium from a soft metal that is very reactive, burn you like crazy, okay, explodes when it touches water, okay, combined with this green poisonous gas, chlorine, combined chemically, and what does it make? Sodium chloride, which is the salt that you have on your food. Very different. A white crystal that is not explosive, not poisonous, not anything, because the sodium and the chloride, they're some things when they're elements, but when you combine them together chemically, they become completely different animals. Completely different.
It's not good for you.
Yeah,
What's that?
I took chemistry. I started looking at the back of my food like, I
guess after I took the chemistry, I'm like, I'm really eating this. This is a chemical, you know. So yeah, I be like that now when I eat certain stuff. After I took chemistry, I'm like, I know this. I'm not supposed to eat. Like all that high
Fructose, yeah.
corn syrup.
Yeah, that's bad too.
I took the sugar class. I was like, well, I don't know.
Yeah. So yeah, potassium. That potassium you said burns. That's probably was potassium chloride or potassium something, and it burns because it's just like salt in the wound. You know, that's going to burn. Potassium chloride is just another salt, but very different from potassium and very different from chlorine. It's a compound, very different. Now, sugar and water, it's still sweet, it's still liquid. Okay, that's a mixture, not a compound. Okay, hydrogen's an explosive gas. Oxygen, the source of combustion. Okay, you mix those together, you make water, and you use that to put out fires. What? Okay, but completely different substance. All right, now, this is what happens on the macroscopic level, okay? On the level where we live and see. Potassium, chlorine, oxygen, whatever, nitrogen. On the subatomic level, we have atoms. Elements are made up all of the same type of atoms, okay? Now, compounds, since they're made up of more than one element, they have different atoms connected chemically to form molecules. So this is the macroscopic level. This is the microscopic level. Macroscopic level, microscopic level. At the very smallest thing, the molecules are those things. One oxygen with two hydrogens attached to it, that's a water molecule. Okay? On the macroscopic level, that's the compound water. Okay? Now, so that's molecules and atoms. Those are the next two words. Now we're ready for this. And this is the one I was just describing. Oxygen, a gas that is necessary for anything to burn, combines with hydrogen, another gas, the lightest gas there is, and is very explosive. Does anyone know what the Hindenburg was? Ever heard of it? It was one of the earliest blimps. Man didn't know how to fly, but they figured if you put a light enough gas in a big balloon, it would lift you. So they started with blimps. Those were the first lighter than air machines that could fly around and move people about. Okay? And because hydrogen was the lightest gas, they put it in. Well, it was on a trip somewhere. People were always flocking out to see it because no one had ever seen these things move before. And it either happened in a thunderstorm and lightning struck it, or it hit something and ripped it, and there was enough friction there to produce heat, and that hydrogen got exposed to oxygen with a little bit of heat, as in lightning or whatever, and it burst into flames. And people inside the blimp, and they were all burned or killed from the fall or whatever. Not a pretty sight. So ever since then, blimps are all filled with helium. Now, on your periodic table, that 8th column over there, that last column, that's helium, neon, argon, krypton, xenon, radon. They don't combine with anything. So helium, the second lightest element, that's what they started putting in blimps. It didn't have as much lift as hydrogen did, but it would not burn. It will not ever combine with anything. Hydrogen, oxygen, nothing else. Okay, so that's okay. Hydrogen, the lightest element, lightest gas, that is very explosive. That's where the Hindenburg came into play. Oxygen, that supports combustion. When they combine together, and guess what? It's never hydrogen, oxygen, hydrogen. Hydrogen, oxygen, hydrogen. Never in a line. Always the hydrogens are at one end, the oxygen at the other end. Okay? That's just the way the electrons, which we'll talk about later, are configured. these share an electron pair, these share an electron pair. Over here and over there, hydrogen, oxygen already has 2 pairs of electrons they don't want to share with anything else. So that's why it does like this. So it's always one end is hydrogen, the other end is oxygen. Okay? This is a liquid, not a gas, and you use it to put out fires. Okay? It's crazy how things work like that. The water molecule composed of 2 hydrogen atoms, 1 oxygen atom, combined chemically. That's what H2O stands for. Now this is something a lot more complicated. This is an organic sugar. It's the simplest sugar we have, okay? Glucose, which, by the way, is the same structure as sucrose and fructose, but it's maybe a little more digestible without hurting the system as badly. And that's what they give you in IVs, is glucose, not fructose. Sorry.
Yeah.
Okay? Now the relative sizes aren't quite right here. Carbon will be much smaller and hydrogen and oxygen fairly much bigger, but they put them all the same size. It's okay. Every carbon will connect to 4 other things, okay? And this carbon is connected to another carbon, another hydrogen, and an oxygen that has a hydrogen on it. Hydrogen only connects to 2 things, 2 hydrogens or a carbon and a hydrogen. Oxygen, I was going to say, yeah. Hydrogen only combines with 1 thing, so hydrogens are always only 1 thing. So this next carbon is also got a same kind of deal, only a little different here, because it's connected to another carbon, but then a hydrogen and oxygen with a hydrogen on it. And this is connected to this one, just like this one, with a hydrogen, oxygen with a hydrogen, to another carbon with a oxygen, a hydrogen, and a hydrogen. Another carbon with a hydrogen, oxygen with a hydrogen, and another carbon. Now this one's a little different from this end. This carbon has 4 bonds to it, but 2 of them go to the same oxygen here. Oxygen needs 2, carbon needs 4. There's 1, there's 1, here 2, and the oxygen has 2. It doesn't have another hydrogen on it like these 2. That is your simple sugar. Okay? Glucose. Believe it or not, it is the simplest one. There are 1, 2, 3, 4, 5, 6 carbons, 12 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens and 6 oxygens. 1, 2, 3, 4, 5, 6. Okay? So it's C6H12O6. Exactly the same setup that you would find in fructose and sucrose. It's just how these things link together would be a little bit different. Now, I don't know this for sure, but supposedly Splenda is almost the same structure, but Splenda doesn't get metabolized like sugars do, so you don't gain weight, but it tastes almost the same. They say, I'm very big on artificial sweeteners, but supposedly it's the most similar to sugar, and it doesn't do anything bad for your body that we know of yet. Okay. Now, way back, one of the first artificial sweeteners was saccharin. And after using that a whole lot, then they started finding out people started having some problems with it. So they sort of stopped using saccharin and went to whatever's in Sweet and Low. And, yeah, and they found things wrong with that. I don't know if they found anything wrong with Splenda yet, but I wouldn't be surprised if in time it does. You just can't play with Mother Nature, you know? She knows how things are supposed to be. But, anyway. So that's examples. These are your elements. These are your compounds. Okay? Fixed together in certain ways, having certain characteristics. Okay. Now, notice I said they bond only a certain number of bonds. Why is that? Well, you need to know what goes on inside every one of these elements. An element can't be broken into another substance but it can be broken into pieces. And those pieces are typically protons, neutrons, and electrons. Very good. Y'all know your stuff here. Okay, protons are positively charged, P positive, okay. Electrons are negatively charged, okay. Neutrons are not negative, even though it starts with N. They're neutral. Neutrons, neutral. They have no charge. What's that? Yes, exactly. And that forms the basis for everything, okay? Because in general, an atom is going to have the same number of protons as it does electrons, because all atoms are balanced electrically, or neutral electrically. Now, neutrons, you can have extra neutrons or not, it doesn't matter, okay? Too much. There are some things that it does matter some. And by the way, the protons and the neutrons live in the nucleus, which is incredibly tiny.
It is.
I mean, incredibly tiny. And yet all the mass is right there. Most of the volume taken up by an atom is by that electron cloud. And the electrons have almost no mass at all. They have a little bit, but not much. The protons and neutrons, each one of them, has something like 10,000 times the mass of a single electron. And yet the electrons take up all the space, and the protons and neutrons are packed together in that nucleus. Okay? So the nucleus is an incredibly dense piece of matter, surrounded by a cloud of electrons, which have almost no mass at all, but they take up all the volume. So that gives the overall atom something to play with. Now, I can remember my older brother coming home from college, and he had just learned this, and his professor said it this way: therefore, most of everything is nothing. Because the space occupied by an atom, all the mass is in that tiny, tiny, tiny little nucleus. The electrons have almost no mass, and around them is just empty space. Empty space, emptier than outer space, just nothing. So most of everything is nothing, okay? But it doesn't act like that. It acts like it's a single entity, but really it's not. And they show in the book the properties. Let's see if they show this. Yeah, there it is. Look at the mass. Okay, the mass of a proton is 1.673 times 10 to the minus 27 kilograms. That sounds like a pretty small number, and it is. And the neutron's just a little bit, just a tiny amount bigger than, or more massive than a proton. About the same size, but a little more massive. 1.675 rather than 1.673. All the rest of it's the same. But then when you get to the electron, 9.109 times 10 to the negative 31, that is a difference of close to 10,000. It's 1/10,000th the mass of these others. Not quite that little, but close to it. Okay, less than 1/1000th of the mass. Diameter, these two almost the same. You can't even measure the diameter of an electron. It's that tiny. But the charge, positive charge here, negative charge there. Now, size of an electron is zero size is due to the lack of any internal structure that we can measure. There's nothing to measure there. It has to have a little bit of size, but there's not enough that you can measure. Anyone can measure, yet. We don't have the capability. Okay. Now, any questions so far? This first is mostly introductory stuff. They left off a slide here. I don't know if it's worth doing or not. Let me go on and do it. Pain in the neck, but we'll do it. Okay. Okay. Here is a hydrogen atom? One tiny little proton surrounded by even tinier little electron. So tiny it hardly makes a mark. And that electron just goes around that proton, taking up all the space of the hydrogen atom, but all the mass is right there. Between 1,000 and 10,000 times the mass in that one little nucleus, and hardly any mass of the electron, but it flies around there. Okay, that's hydrogen. Here's carbon. Carbon's pretty simple, but it's a lot more complicated than hydrogen. Carbon has, what color do you want your protons to be? Black or something else? Second? Black? Okay. Blue? Okay, blue. Light or dark? Dark? Okay. Is that what you said? Okay. All right. Dark blue. Okay. Carbon only has 4 little protons. I'm going to make them by pluses. No, that's not right. No, 6. 6 little pluses. Okay. Now, these are really crammed together. I just did them big enough so you could see. It also has 6 little neutrons. Now, I'm going to make the neutrons just circles. They have no charge. Okay. Now, all those are packed jammed into a tiny, 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 tiny little nucleus. Okay. Now, the electrons, just so tiny you can't see them hardly. 2 of them here in the inner shell, and that's all. Except for hydrogen, which only has 1 in the inner shell. Every other thing has 2 electrons in the inner shell, and that's all. Then they go to the next shell, and I'll just do it like this, and carbon has 4. The inner shell is complete. It doesn't mix with anything. Only hydrogen, that 1 that's in the inner shell, it mixes with whatever it can get to. Okay? So I meant to do all these things in different colors. I just gave them different symbols. Sorry about that. Okay. Now, remember I said carbon could connect with 4 other things. Why? This electron pairs with 1, pairs with 1, pairs with 1, and pairs with 1. There's this 4. Now, oxygen can connect with 2 things, so that 1 oxygen at the end of sugar, 1 oxygen can pair with 2 of those. Well, that's what happens with carbon dioxide. The carbon in the center and 2 oxygens, 2 here and 2 there. Only these will be, this one is in line. This will form a linear type thing, not this. I should take that one off. Okay, but you don't have to worry about the structure of it, but that's what's happening. And that's why they only combine with certain numbers. Okay, 2 oxygen spare electrons combined with 2 of the spare electrons from carbon. The other 2 spare electrons from carbon will do with 2 oxygen spare electrons. That's why they bond, and they bond really tightly. Okay, so it could be 1 thing each, or some of them could be double. Occasionally, you'll see a triple bond of a carbon with another carbon, and that takes 3 of each of their electrons, only 1 available for something else. Okay. Now, a guy is mentioned here named Ernest Rutherford. How we know that all the mass is congregated in a tiny, tiny, tiny little nucleus, and most of everything else is empty space, okay, is Ernest Rutherford. Before that, they called it the plum pudding model. They thought that the nucleus, whatever that was, protons and electrons, was like a pudding, and the raisins were the electrons just stuck around in the pudding. Okay, so Ernest Rutherford was going to verify that by taking, now one of the things with a very massive nucleus is gold. Okay, really, it's way down in the periodic table. Several, like the 6th row, somewhere way down there. Okay, But gold can be rolled out into very, very thin foil. Have y'all ever heard of gold leaf? Yeah. That's very incredibly thin, and you just take something and rub it on something and it makes it look like it's gold because it has just a very thin layer of gold. Gold is so brilliant in its appearance, it makes the whole thing look like it's gold, where it's just a very thin layer. So he took down those very thin sheets of something like gold foil, and he was going to fire some alpha particles, which are 2 protons, 2 neutrons, no electrons. So they're an ion. Fire that at this and watch them bounce off. And he was going to get an idea of, how things work. Much to his surprise, most of those alpha particles went right through the gold foil. Didn't hit a thing. But the few that did bounced almost straight back or at big wide angles. He said, what is going on here? Well, that's because the nucleus, that's where all the mass was. That's the only thing you could bounce off of. All the rest of it was nothing. Empty space. So most of them went right through, except every now and then one would hit a nucleus and bounce off. Okay? And at a pretty good angle, too, because the nucleus is positively charged. Protons and neutrons. Neutrons have no charge, all protons. And then the alpha particles are 2 protons, 2 neutrons, so they were positive. So they bounced right back. Okay? And that's how we found out most of everything is nothing. It just went right through the gold, which is a very dense metal, went right through it. Okay. So that's what Ernest Rutherford did. Now, boy, they just jumped rabbits in this. Okay? Let's now start talking about and we'll start with the name of it, and the book uses states. Most physics books don't use these anymore. That's what we called them when I was growing up, the 3 states of matter. Okay, have y'all ever heard that? What are they? Solids, liquids, and gases. Actually, the better word for them is 3 phases of matter, solids, liquids, and gases. Because now that quantum mechanics is here, and who understands that anyway, the word state is used for a different thing. That's energy level and stuff like that. That's called the state. So we use phases for solid, liquid, and gases now. But there's actually 4 of them. There's another phase called the plasma, okay, which is different, okay. So let's start with, and those are the 3, this book calls them states, so I'll call them states of matter. Solid is a substance that has a definite shape and a definite volume, okay. This thing right here is a solid. It has a rectangular shape and a definite volume, okay. The tabletop, the chairs, most of what we see, solids. A liquid, you had some in there, right? Okay. Now, when it was in the cup, it had the shape of the cup. When you drank it, it got the shape of your throat. Until it got to your stomach, it took the shape of your stomach, okay? It varied its shape, but it always had the same volume. Okay, if you started out with 32 ounces, you had 32 ounces. When you drank it, you drank 32. Yeah, whatever. It always had the same volume. The third of these is a gas. Now, if I were to, you mentioned ammonia, didn't you? You ever had ammonia in the house? Okay, you ever open it up and forget to close it back? Not for very long. Why not? Yeah. Boy, you'll smell that stuff if you leave that top off. Okay. The reason is, if I open a bottle of ammonia over here and I have to go make some copies, y'all just wait here. After a while, your eyes would be burning and stuff, and then yours, and after a while, even yours, because that ammonia gas is going everywhere in the room. After a while, when I walk back in, mine would be burning because I said, I shouldn't have done that, should I? Okay? The reason is the gas fills the whole volume of the room.
So is it safe for people to put chemicals like in? I mean, I've seen people put chemicals like on their stove to make fresh.
Yeah.
They
Oh,
like
you
their
talking about
house
smells
and
and
stuff.
stuff.
I done heard somebody do that. I'm like, you gonna set your house on fire?
Yeah, you
Yeah.
boil it.
Now, what do they put?
Like cleaning products.
Oh.
Like say
Yeah.
for example,
Oh,
Mr. Clean, you
yeah.
put it in water and
Yeah. And they're trying to make it smell like the house is clean? That's sort of a cheap way of doing it, isn't
That's
it?
not safe, is
Yeah.
it?
I wouldn't recommend it. Now, my wife did get some, I don't know if she bought them or someone gave them to her, some aromatic oils that you put the sticks into, like skewer sticks or something, and then they come up, and boy, when she first did it, you could hardly stand it in the, I think it was in the kitchen, and even 1 or 2 rooms away, you could still smell it. Now it's sort of mellowed out, so and we have one up in our bedroom too, and they're nice fragrances, so they're safe. But you know, I'm not sure about the cleaning supplies. Okay. Yeah.
Yeah.
Oh, you better watch that. Yeah. What you're forming is some chlorine gas, which is poisonous, because some of that's actually coming out of that. You don't mix much of any kind of soap with Clorox. You know, yeah, because
My mother-in-law did that.
you have to be careful with that. And things like Tilex and things like this, if it's mildew killer, it's probably got Clorox in it. If you mix that with a detergent, don't breathe those fumes very long, because
Oven cleaner is strong too.
the what?
Oven cleaner.
Yeah. Oh, yeah. Very, very. And then the heating in the oven makes it even more pungent. Okay. So a gas will take the shape of any container and take the volume of any container. A liquid takes the shape of the container but keeps its own volume, and a solid keeps its own volume and shape. Now,
Time to go.
what's that?
Time to go.
Oh, no! Let's do this one slide, because this slide shows what I was just talking about. Okay? Not that one. Yeah, okay, it's the next one. Okay, from current slide. All right, let's go. Yeah, here we go. Now, this is a solid. Now, this isn't a great picture of a solid, but it's okay. 2 substances here, 2 types of atoms, so 2 elements in here, the dark ones and the light ones. And it shows that the dark ones can connect with 4 others, and the light ones connect with 4 others. Okay? This could be sodium and chlorine. Okay? Sodium chloride. It's not quite got the same thing. But notice there, every element, every atom has a place. And it's connected to the next adjacent one and fixed in place. That's what makes a solid a solid. It has its own volume and its own shape. They aren't free to move. They have a little bit of freedom in that they can vibrate. But that's all. They can't move around. They can just sit there and vibrate. Now, while that's important, what happens to a metal when it heats up? Okay, before it gets that hot. Okay, it could, but it expands just a little bit. Not much, but and that's because the vibration, as it heats up, the vibrations get stronger, so it expands a little bit.
Did you see on the news where it had to be up north, it was really cold, it was -degrees, and the light pole was shaking.
Yeah.
It was so cold.
Yeah. And part of the reason for that is when it gets cold, it shrinks. Okay? So the wires between the poles are pulling them closer and closer together, and that was a tension there. And that's why, because they did not figure it was ever going to get that cold.
Yeah.
If you run your power lines or your phone lines or whatever in the summertime and it's really hot and you get them really tight, then that next winter, it'll pop that post. It will break that telephone pole because it's shrinking. And that's what it was doing. It was vibrating like that because it was that, the tension in the line was that much. So a liquid, they keep about the same distance from each other, but they're not fixed in place. These are fixed in place with the same distance, approximately the same distance from each other. Liquids free to move past each other, but they stay close. The proximity is still there, but not the fixed location. We call this a crystal structure. This has no crystal structure. Whereas the gas molecules, they just go wherever they want to. Occasionally they may bump into each other. This shows them way more. And then they just bounce off each other in an elastic collision. You know, they don't lose any energy. They just bounce off each other and keep going. These will bounce off each other too, more frequently than that will. But that's the difference, solids, liquids, and gases. We'll start next time with properties of solids. No new problems at the end of that section, so we'll pick up and go from there next time. Did I use all the time? I didn't want to cheat you out of any of your tuition dollar. Okay. All right. All right. Good deal. Good class.
Yeah, that's what I was about to
What's that?
The test.
Yes. And you said you didn't have yours. So I can't return them until I get them all back in. But what did I do with them? That shot me. Okay. Oh, there we are. Okay. I'll put this on top. All right. All right. I don't think I have yours yet either.
No.
Okay. So I need these back. I had a work study student who marked them, and she was going to take over the thing, you know, and she didn't. And I've never had her before, so she didn't know any better, but I just wanted her to circle anything that was wrong or that she had any question about. But she was going to decide how many points and everything, but I fixed it. So if you see extra marks on there, that's why.
So just round.
Huh? Yeah, rounding, yeah. That's the only thing. She wrote the rounding on there, I didn't. If she becomes a teacher, she's going to be a toughie. I think so.
What's she trying to teach?
Huh?
What she's going
I
to
don't
teach?
know. I was just saying if she was going to be one.
That's what when I was doing, I was like, should I round, should I not round?
Don't worry, yeah.
That's what I'm wondering
If
about.
you got
'Cause I
the right
think-
answer, whether it's round
That's
or
why I
right or
need
not.
the extra sheet.
Huh? Yeah.
I have a question. Thank you.
All right, glad to. Good job. Did you have a question to say?
I do.
I didn't always have a chance to go back and check your work. I try to do that, but
I think this is exactly how it came up when I put it in.
okay, this is number 2. Let's see what number 2 is.
Which is not okay, but I'm just wondering because it just came up exactly like that.
Okay, yeah, but it's okay.
Okay.
Yeah. That's the only one that you got counted off.
Yeah, let me see. I don't know how to do that one.
My
I
guess is
thought I was going by
I
the
think
book.
you divided. You got it reversed. I bet you if you put the other one over the other one, you get the right answer.
Let me see.
Try it and see. Yep. The answer is rounded.
I couldn't see an example of that, how to work it out in the book. I
Yeah.
thought I went out with the book.
I can't talk about it too much. but
Yeah, I
still,
understand.
can't do it, but, yeah. It has a formula. One of them equal to
Right,
U
yeah.
times the other.
In chapter 5.
And
Let me just see if it's the one that I read about it. I wrote it in my book. Still square.
Yeah.
Yeah.
Okay. See what goes on top of the first one.
All right, bye.
See, this is the normal portion. That's the first one.
Oh, yeah, I can help.
All right. Good
Thank
deal.
you.
And hopefully, when I get them all, I'll give them back to you.
Okay.
And then at that point, I can work them on this. I can't work on them
But
here.
it's not gonna be like comprehensive for the final, right?
No, the last test is your final test. Right. A lot of this stuff does build on itself, so things that we used in the first chapter, we used in the next one, and we'll use again. Some of it doesn't do too much of that, but so whatever the last chapter, that'll be it. All right, good deal.